Okay, let's do another one. So here now we have a little bit more complicated loading setup, and we're asked again to draw the shear bending moment diagrams for the internal forces acting along or within this beam, right, for the given loads. So we know now that we're going to need to just figure out how many sections we need to come up with, right, in order to identify those loads. And we've already established that we know that everywhere the loading condition changes, right, external loads, whether it's moments or forces, change, then we're going to have to probably have a change. We will have a change in our shear bending diagram. So from here, from this one, we could see, for example, that there's a couple of different sections that we're going to need. So we're going to call this one section 1, going from here to here. Then nothing changes, so then we can think of this one as section 2. And then this last section over here is section 3. Maybe it's clearer to just write all those down below. Again, I'm sure I could edit these videos. But anyway, all right. So those are our 3 sections. So let's consider each of those cuts independently. So we'll draw a free body diagram for section 1. Right? This is for X, basically between 0 and A being along the length of the beam. And again, this is anywhere along that distributed load, right? So anywhere, and I'm going to basically get a free body diagram that looks like this. I'll have AY, I'll have W, whatever value that is, internal loads, a normal, shear down, and a moment. And again, this is our distance, right, X here. So if you're not convinced, you can draw this free body diagram for a section that's just like this or like this, but they will all look exactly like the one I just drew. So now let's just write up our equations of equilibrium. So again, we know that the sum of forces in the x direction will tell us that n equals 0. Sum of forces in the y direction, AY. And now I have the distributed load, and I'll multiply it by the distance over which that load is acting, which is x, just like we've done before. And then minus V equals 0. So now shear is no longer a constant, right? V is equal to AY minus WX. So I think this is the first time now that the shear is a function of x. And we can also now draw the one for x for section 2, right? So this will be section 1. We'll call this one section 2. And this is for x greater than A, but maybe less than B, right? So we'll draw this free body diagram. Now we'll for sure include the whole distributed load acting over the length A. Still have our reaction force AY, right? And I'll just leave P out of it, so just before B. And so this is N, this is shear, this is now the moment. I guess for completeness, we can see that sum of forces X will be that N equals 0. What we really want to know is what's happening in terms of the shear. So sum of forces Y, now we have AY minus W, and now it's acting over the whole length A, right? So this distance here is A. This is our X now. Minus V equals 0. Solve for V. So V is equal to AY minus WA. So now it's no longer a function of X. And now shear in this section is a constant, right? These are just numbers. If we knew what A and AY were, right, then we could solve for these. And now let's look at what's happening beyond B. So we'll draw one more, section 3, and look at what happens when X is greater than B. again, we still have the full distributed load. We still have AY. Now we have P acting, right? And shear and the moment. And now this is our distance x. Here, this distance is A, and of course this distance here is B. And now again, just write out your equation. Sum of forces x, normal is 0. Sum of forces y. We have AY minus WA minus P minus V equals 0. And so now V again, right, is just AY minus WA minus P. A constant, but not the same constant, right? Here, it's a different constant.